with our current webinar on fracture mechanics using meso-scale universal load frames. Our speaker today is Dr. Alex Arzumanidis from Psylotech, and he has quite the passion for mechanical load frames. Let me give you a little bit of background on Alex. He got his PhD from the University of Texas, and after that went on to work with Schlumberger in their research and development facility down in Houston. After his stint with Schlumberger, he started his own company, which was focusing on high-resolution sensors. And from that, he's decided to start this company, Psylotech, which basically is based on those sensors. And I'll let him tell you more than that. But Alex is a unique individual who has quite the passion for mechanical testing, and it's a pleasure to hear him talk today, I have to say. So with that, I'll turn it over to Alex Arzumanidis.
Thanks, Tim. Thanks very much. And I very much appreciate everyone taking the time to spend with us today as I go through this instrument that we've produced. So I just want to give you a little bit of a background. Tim gave you a bit of background about myself. Actually, at Texas, my thesis was in fracture mechanics and viscoelasticity. And in fact, the company does two main things. One of them is helping people simulate plastic and rubber, so not only viscoelastic simulation, but the other thing and the aspect of the company that we're going to be talking about more today is this small-scale universal test machine. And as Tim said, we sort of developed it. It leverages the high-resolution sensor technology, so there's certain unique things that you can do with the instrument, and I'll show you how that's valuable specifically with fracture mechanics. So the frame itself actually came out of a project, an SBIR project with the Army, where they wanted to have a flexible load frame that was capable of going to being used with different kinds of microscopes and being able to use leverage digital image correlation to get small-scale samples tested. So as a result of SBIR, this instrument came out essentially. So this has a few years of development together with collaboration with the Army Research Lab and also a professor down at the University of Illinois, Yannis Chasiotis. So generally, this is the instrument. It's meant to be a universal load frame. So think of it as sort of as a mini Instron or a mini MTS machine. So anything you can do on a large scale, you can do on a small scale. So any experimental fracture mechanics a test that you can think of, you could do on a small length scale. The trick is that the key of this is being able to use digital image correlation and microscopes to be able to get small scale images so that you can see what's happening on these different length scales. So one of the keys that you'll see about this instrument is that, especially with optical microscopes, it keeps the sample from moving out of plane, which means you can leverage optical microscopes in these kinds of experiments. Has a huge advantage for fracture where things happen quickly to be able to take an image quickly with an optical microscope as opposed to a rastering type of a concept like an SEM or an AFM. In any case, this is the instrument that I'm going to show you today, and in fact, to talk a little bit about using digital image correlation to help with fracture mechanics specifically. There are three ways that you can, I'm going to talk about monitoring the crack growth. One of them is going to be basically using digital image correlation as a crack tip opening gauge. Another one is using the correlation coefficient to help you track the crack location. And then the final one is going to be leveraging the instrument itself and the high sensitivity of the sensors to get the specimen compliance. So the basic concept here today is to talk about how to use this instrument to do fracture on small length scales. So I suspect that everyone is quite familiar with the technique, but just in case they're not, I wanted to sort of explain a little bit about what digital image correlation is. The idea here is that you can get down to maybe, let's say, 0.1 pixel resolution or even better of features and images of the displacements of features and images from one picture to the next. And of course, if you have a displacement field, then you're able to calculate the strain field. So it's a way way, a non-contact method of being able to get the full 2D surface strain field on the surface of a specimen. So the instrument requires this digital image correlation to really be able to work on the multiple length scales. And of course, you need to be able to take pictures, so you need microscopy. So there's optical techniques and also AFM and SEM. But you see sort of the images on the bottom. You can tell, you know, these two images, if you just look at them with your eye, there's really no difference in the strain field. But when you use digital image correlation, you can see that there's, you know, displacements of pixels of features in the images. So that's the basic idea of digital image correlation. Now, specific to the instrument and microscopy, one of the big values that we bring to the table with the instrument is under optical microscopes, if you have a little bit of out-of-plane motion, you lose focus, and then you can't use DIC. But optical microscopes have some huge advantages. For example, you know, if you can get images down to the optical resolution of light, which is about 250 nanometers, so you can see features that are as small as 250 nanometers, and with DIC and the 0.1 pixel resolution that I mentioned before, you can actually see 25 nanometer resolution of the displacement field. So you can see those 250 nanometer features moving by as little as 25 nanometers. It's quite a powerful technique for small length scales, and it doesn't require a vacuum chamber like an SEM would, for example. And you also have other advantages like fast image capture. So if you want to see things moving a little bit more dynamically, you can. This instrument can also go into an SEM. Of course, the SEM offers a higher resolution, but it's tricky to use with digital image correlation because you have to keep track of drift of each of the pixels. So it can be kind of tricky to make that work right. So, but it is another option. And of course, you can also put these instruments that I'm going to talk about today under other kinds of microscopes to get the images. But let me get back to the sort of focus of this talk, which is to talk about fracture samples. And as I mentioned before, it's a universal load frame. So any kind of a test that you can do on a macro scale, you can do on a small length scale. And we make the system as flexible as possible. There's sort of a T-slot interface so that even if the array of grips that we offer isn't good enough, you can make your own grips. It's a very good tool for experimentalists to try new things with. Here I just show a few examples. There's a compact tension test, probably the most recognizable fracture mechanics test. There's grips for Arcan specimens, which of course will give you shear, so mode 2, mode 1 types of fracture, or mixed mode in a pretty easy way by simply rotating the grips around and installing them into the system. This is another sample that actually I did my PhD thesis on, which is this UCSB sample, which is a mixed mode sample for, and in this case it was for interfacial fracture toughness of an adhesive joint. So, but this list could go on and on. Like I say, anything you can do on a large scale, you can do with a small scale. But let me give some examples, a few results. This is actually from a 3-point bend test. So the center of this image is where the load was applied, and of course the outer sides were held as well. And it's really quite interesting to me. It surprised me when I saw this. We didn't really, of course, with digital image correlation, you have to be careful about how you apply a speckle pattern. And we just tried this with a 3D printed plastic sample. Turned out gave pretty good results in that we were able to see the strain fields ahead of the crack tip. In this case, this is sort of the shear strains in front of the crack tip, and in a mode 1 opening. So it's quite an interesting result. That's if you don't have digital image correlation, it's hard to see. In this case, I'm sorry. Another thing I want to point out, which will be interesting for later, is that the software, the VIC2D correlated solution software for digital image correlation, it wasn't really able to do a good job in the middle where the crack was being created because the correlation, because the DIC doesn't work very well when new features show up on the instruments, in the images. I'll talk a little bit more about that in an upcoming slide, but I just thought that was an interesting result, the way that you can see these are the kind of pictures you might see in a textbook, but there you have it in your experiment. Of course, another way of taking advantage of digital image correlation when you're with these under microscope tests is to just use the displacements that you get from DIC as a crack tip opening gauge. So this is an example, actually it's the same sample, the same 3-point bend mode 1 sample that we just put a block above and below, and we saw how much that block moved on average compared as the crack was growing, and that gave us a crack tip opening displacement. So, just a pretty standard technique, but with a little bit of a twist, adding DIC instead of having to clamp on a crack tip opening gauge. Another interesting technique that I've seen in the last few years, oh, I went up 2 slides, sorry about that, that I've seen in the last few years is, digital image correlation has a problem when new features come up. The way that it basically works in a very rudimentary way is you sort of pick a pixel, and then the software takes a curve fit of the pixels around it to know how much that one pixel moves from image to image. So in this case, you can see there's sort of a line of pixels, and this is the grayscale level, and that's how it knows that it moves and how it can track it to below a pixel resolution. The problem happens when there's a crack and you end up breaking this. It's very difficult for it's difficult for digital image correlation to find how much motion happened because there's a new feature that's different from one sample from one image to the next. So what happens is there's a correlation coefficient, which is a sort of degree of not accuracy necessarily, but it's a degree of confidence that the DIC is working properly. When that gets too high, then you can kind of see if it gets very high that there's a problem, and that very problem can be used to track the crack length. And I saw some people doing this back at the MS&T in 2012, some folks from Los Alamos, and I'm sure other people are doing it as well, but that's where I first saw it. So we talked about using the crack tip opening displacement. We talked about using the correlation coefficient to get crack length. Another interesting way to do it is to just use compliance of the specimen. In this particular case, this is the USB sample that I used in graduate school, and we were able to track the crack length based on the displacement measurement and the force measurement. And you can see sort of the crack length compared to the compliance. Theoretically, it's a linear relationship. You have to be very careful about friction at the contact points, but we were able to get it quite close with this kind of configuration with these 3 rollers and a kind of a triangular point. The triangular point was important because if we didn't have it, the specimen, it was a fatigue test, could walk on us. And then as it walked, as it kind of rolled left to right, it looked like the crack was growing when in fact it was not. So specific to this instrument, we have much higher precision than I was able to do in graduate school. So that increased precision should help with this kind of frictional effect. The other thing is that we have extremely high resolution sensors. So higher resolution sensors allows for better resolution of the compliance. So let me talk a little bit about the sensors themselves and the instrument so you can get an idea of how we accomplish this. Essentially, the displacement sensor is an inductive voltage divider. You can see on the right here, there's 4 inductive coils located strategically such that the average location is in the center. So we're actually measuring the displacement on axis. Sometimes when you want to get really fine sort of nano positioning of the actuator, people might, it's tempting to just put a nano resolution encoder on the side, but then even tiny tilts or pitches can affect what looks like a displacement on those kind of length scales. So by positioning the displacement sensor in an X configuration like this, we're actually measuring the displacement on axis where the specimen is getting loaded. Then we also have a capacitive load cell. Now the key to both of these, again, this is a capacitive load cell that is in a capacitive bridge instead of an inductive bridge. But the key to both of these configurations is that we end up with 400 or 500 millivolts per volt of sensitivity. We have much more signal to work with, but we condition it similar to the way one would condition a strain gauge, so that we're able to get, we have, over 100 times more sensitivity than a strain gauge, similar electronics, so we're able to actually get more resolution out of the sensors. So that's sort of the core technology difference of this compared to, let's say, a macro scale instron, is that we have this extra technology that allows for high resolution, which of course has other benefits, like if you have a lab where you have different people running different kinds of tests and they have different load ranges, you don't have to keep swapping out the load cell to cover different load ranges because you have so much sensitivity in this load cell. Similar with the displacement sensor, you can have the same setup handling, nanometer or tens of nanometers of motion, or pulling on an elastomer 30 millimeters. So that's the advantage, sort of the flexibility of this load frame. I'm just going to go through a few sort of specs of the systems just so you can have an idea. This frame is sort of the standard model. It's a 2 kilonewton capacity. Again, we're very careful. You can kind of see the four inductors that are used for the displacement sensing. But we're very careful to keep everything symmetric. The ball screw is on axis, the direct drive ball screw, so that the nut is directly tied to the motor's rotor. And everything is completely symmetrical. The ball guides are in the plane of loading. Everything is on axis, which is the exact reason why things don't move out of plane when you run the test. So that symmetry is very critical for keeping things in the field of view of an optical microscope. The nice thing about the actuator, I mentioned is direct drive, but very fast. The standard load frame is about as fast as sort of a standard servo-hydraulic load frame. Not as fast as a servo-hydraulic that's been tweaked for high speed, but still it's much faster than a typical screw-driven load frame. And it's fast enough that you can do things like load control tests. And it's also nice because it has a very, very large stroke in combination with the high resolution of the displacement that we have. There's another version of this. This is actually the system that was built for the Army. It's similar, but it's smaller. And it's extremely high precision. In fact, the whole load frame, the linear guide, it's all machined out of a solid block of titanium, so that everything is very, very well aligned right out of the box. It also features this YZ stage that helps mounting small-scale samples. When the samples get very, very small, it's a big challenge just mounting them in the first place. So here you have a picomotor controlled. Picomotors are essentially a open loop 30 nanometer positioning device that controls the YZ stage so that you can mount the sample more easily. But again, this is meant to be a multi-length scale, multi-force scale kind of an instrument with different kinds of grips that we offer, but also it's a universal load frame that people could make their own kind of grips for their own special needs. And of course, we're interested in helping if they would like our help in building those grips. So that was what we call the nanotest system. Another option that actually both of these systems, all of our systems have, is you might say only one of our crossheads moves and the other one is fixed. We did that because it keeps the alignment clean. The only problem is that sometimes if you're pulling on a sample, it might leave the microscope's field of view. So what we do is we also offer a sort of a secondary stage where this secondary actuator is similar to the primary actuator. And in fact, it's slaved to move exactly the opposite direction, or actually at any ratio compared to the main actuator. So you might be familiar with load frames where both crossheads move at the same rate in equal and opposite directions, which is great if you're looking at the middle of a tensile sample or something like that. But if you want to look at something that's not the middle, then you're kind of out of luck. What you're looking at might move out of the microscope field of view. Here you can slave a ratio of this to the other, to one actuator to the other actuator, to keep whatever area under the microscope that you want. That's also useful if you want to do a beam bending sample where you definitely don't want them both crossheads to be moving at the same speed, because then you'll definitely lose what you're looking at. So that's the secondary actuator. There's a couple of other things this is actually my second to last slide. I appreciate your patience, but our goal as a company is to offer experimentalists a lot of flexibility to do different things. So we also, the systems themselves have flexibility as well when you, that you can configure them a little bit differently. So for example, they can be a vacuum rating so that it can go into a scanning electron microscope. We can make a faster system. Believe it or not, we can get to 1 meter per second with 150 meter per second squared acceleration, which is pretty fast out of this small load frame if we extend the motor stack and put a 10 millimeter pitch instead of a 1 millimeter pitch. You lose a little bit of force capability, but if you need speed, we can tweak it for speed. We can also put that same YZ picomotor stage on the MUTS. That gets you a lot of the benefit of the nano system without the cost. And then there's also this brand new, what you see at the bottom there, we're assembling the first one, a 10 kilonewton version. That ruler at the bottom is actually a 1.5 foot long, so it's a much bigger frame. Still small relatively, and it can go under a microscope, but it could never go under an SEM. It's too big and heavy. But that frame, like I say, is a 10 kilonewton capacity. That's really this is my last slide. I appreciate your time. To summarize what I talked about, we have this miniature universal load frame. It's meant to enable all kinds of different experiments in multiple scales in force and displacement and rate. It can go very fast and very slow because of the ball screw actuator, the servo-controlled ball screw actuator. It doesn't have a gearbox, so it's quite fast. It can has a large stroke. You can get down to 2-3 nanometer closed-loop control on some of these systems. And the stroke on the system is 40 millimeters, so you're talking about 6 orders of magnitude of displacements. And of course, the key to this is digital image correlation and using microscopy to obtain the images. I mentioned also, just to summarize, 3 ways that you can use the system and DIC to track crack length. You can use DIC as a crack tip opening gauge. You can use a pore correlation coefficient to indicate to you where the crack is on the surface. And then the last way is using the high resolution technology unique to Psylotech to be able to track compliance. So that's the end of my presentation. I don't know if there's any questions, and